Hi, I'm Kevin Smith, a research scientist at MIT working with Josh Tenenbaum, and today I'll be telling you about some recent work we've done to reverse engineer infants' early physical understanding. As adults, we understand physics very well, which allows us to easily interact with the world. With little effort, we can catch and throw balls, pour our morning coffee into a mug, or stack dishes in the sink. But in contrast, even the most advanced robots cannot act with the same flexibility and robustness that humans do. While some can perform well in specialized settings, none are able to generalize to entirely new situations the way that people can. So how can we build agents with a flexible, robust physical understanding? Well, one hint might come from how young children develop their knowledge about the world. If we look at the developmental trajectory of infants' understanding of physics, we find a lot of early structure, but also important learning throughout the first year of life. Beginning at about 3 to 5 months of age, around as early as we can test their knowledge, infants demonstrate a basic understanding of the world that we often call core knowledge. They appear to know that objects exist and that those objects don't wink in and out of existence, can't be in the same space as other objects, or move along smooth spatiotemporal paths. Slightly later, they understand the difference between solid and non-solid objects, and that an object is supported and won't fall only if there's another object underneath it. But despite this early structure, understanding how those principles apply to specific objects comes later. For instance, until about 10 to 12 months, if one object, like a toy duck, goes behind a screen and another object, like a toy truck, comes out, infants don't notice the difference. While there are some conditions under which they will notice object changes earlier in life, those don't go as far back as the core knowledge I just talked to you about. And it's not until slightly over a year that infants realize the shape of an object can affect its ability to be supported, like how the L-shaped object in the upper right has its base supported, but a large mass overhanging that's going to cause it to fall. Together, this suggests that infants might start with a core shape representations that they need to learn more about in their first year of life. When we think about how to design artificial systems that understand physics, we also have to consider the trade-off between building and structure and learning about the world. But where along this spectrum should we be? Well, this is an empirical question, so here I'll talk about two of our attempts to build models of core knowledge of physics, using similar principles but differing in how much structure is built in versus learned. Each of these models has its own strengths and weaknesses, which illuminate the trade-offs involved when considering how to design agents that understand the world. The first approach, which I'll spend more time on, is a more structured top-down approach with only a little bit of learning that we call the Approximate DeRender Extended Physics and Tracking Model, or ADEPT. The second approach, called the Physical Object Discovery Network, or PODNet, has some core knowledge of physics, but is much more focused on learning how to extract and track objects based on their motion in a video. We'll test both these models in people using a paradigm from developmental psychology called violation of expectations. In this paradigm, we show the model or people one of two matched videos, where one contains a physical violation. For instance, in the video on the left, the screen moves through the chair, whereas the chair stops the screen on the right, as it should. In the developmental psychology literature, this paradigm is used to test whether infants understand a physical principle by asking whether they can differentiate the two scenes. If infants look longer at the screen on the left, this suggests they find the violating scene to be more unexpected and therefore understand the principles about object solidity. Similarly, if our models are reliably more surprised about the video on the left, for instance, by putting a lower predictive probability on that video, then we might assume that they have a representation that includes those core knowledge principles as well. Here we tested 8 different kinds of violations, all inspired by developmental experiments used to probe infants' core knowledge. For instance, in the create and vanish scenes, objects appear or disappear behind a screen, testing the principle of object permanence. In the overturn and block scenes, objects appear to move through other objects, testing the principle of solidity. And in the discontinuous and delay scenes, objects teleport or move instantaneously behind screens, testing the principle of spatiotemporal continuity. However, an important feature of humans' understanding of physics is that it's generalizable. When infants perform one of these experiments, they have presumably never seen objects behave in that non-physical manner before, and have likely not seen the specific objects used in that experiment. Yet, they're able to reason about how those objects should act nonetheless. Therefore, we built a training set that contains no physical violation and uses a set of objects separate from those that appear in the test videos. We used objects from ShapeNet, a commonly used repository of object meshes that contain a number of instances of categories like chairs, planes, or cars, but held out 1/5 of the categories and 1/5 of the instances of each of the categories that we did use for training. So we can use those shapes to test how well our models extend to objects that they've never seen before. So how well does ADEPT work? The ADEPT model has 2 parts. the approximate derender, and the extended physics and tracking. The approximate derender is used to extract object information directly from video frames. It uses convolutional neural networks to first segment the image into areas where it believes objects to be, then determines the properties of each of those objects as a symbolic description that includes information about that object's location and size. Crucially, this representation is approximate. Just as infants don't appear to use information about precise object forms, the approximate derender treats all objects as having simple shapes, either as ellipsoids or cuboids. This allows adepts to generalize to new objects more easily and more quickly than if the derender was required to learn the shape properties of each new object. We use supervised training on these videos shown before to train the derender to output these representations. The second part is the extended physics and tracking, which uses the output of the approximate derender to track and update its beliefs about the state of the world. Based on the human intuitive physics engine that suggests that people have the capability of probabilistically simulating physics, this module uses a particle filter to maintain a distribution of beliefs about the current state of the world, and a noisy physics engine to predict what it expects to happen next, then compares those beliefs to its next observation from the approximate derender, and uses that observation to update its beliefs. In most cases, this will cause the model to reweight its beliefs towards world states that better explain its observations. However, in some cases, the model observes something entirely different than it expects. An object might have appeared, disappeared, or teleported. In this case, the model can resample the properties of objects, including their existence, from a scene prior, which allows the model to change its beliefs to align with observations. However, this resampling is expected to be particularly rare, and so is low probability in the model. Here we assume that the physics knowledge is built in, and so we don't train the dynamics module at all. Given this framework, we can extract the surprise from the ADEPT model as the negative log likelihood of each new observation based on the expectations of the extended physics model. This provides us with a quantitative measure of surprise that evolves over time as the model watches a scene. So how does the model perform? Well, let's take a look at a couple examples. First, let's see how ADEPT performs when an object disappears. On top, you can see two balls move behind a screen, but only one comes out. Finally, the screen rotates down to show nothing behind it. On the bottom, you can see the model's distribution of beliefs about the location of the two balls. Note that once the ball leaves the screen, it continues to be tracked, but the other ball is assumed to still be there behind the screen. When that screen comes down, that belief can no longer be sustained, and so ADEPT assumes the ball doesn't exist. In the middle, you can see ADEPT surprise over time, where there's still some small uncertainty during object tracking, and it's slightly surprised when the second ball doesn't roll out from behind the screen. It's not until it's had to reevaluate its beliefs about the existence of that ball that it becomes truly surprised. Next, let's look at one of the overturn scenarios. Here, the screen goes up to include the ball, then continues to travel back through where the ball was supposed to be. Then it rotates back to show that the ball is still there. In the bottom plot, note how ADEPT believes that the ball must no longer exist when the screen moves through that space, but then sees that the ball does in fact exist later, and that leads to 2 times that it's surprised and 2 spikes in its surprise signal. We can test how well ADEPT performs overall by comparing it to alternate models that are mostly unstructured and learn the dynamics directly from pixels. We compare these models using a relative accuracy metric. We compare the surprise the model registers to each video from matched scenes and count the proportion of times the model finds that the violation scene is more surprising than the control. ADEPT performs well above chance overall, outperforming the baseline models, which are at or only slightly above chance. It's as good or better than all of the models, other models in 7 of the 8 scenarios, and it always generalizes better to novel objects, including novel shapes of categories that it's never seen before, or new categories or basic geometric shapes or toys like toy bunnies or trucks. But although ADEPT outperforms these baselines, we might ask, does it do it in a human-like manner? To test this, we asked participants to register surprise to these videos in 3 ways across 3 experiments. In the first experiment, participants watched a video on repeat and registered how surprising they found that movie on a sliding scale, providing us with fine-grained ratings of surprise. In the second experiment, participants watched the same videos, but pushed a button wherever a surprising event occurred. And this provides us with momentary timings of surprise. In the third experiment, participants again watched the same videos on repeat and were asked to check boxes describing what was surprising about the scene, providing us with explanations of surprise. Here, we're only going to compare ADEPT to the how and when experiments, the first two. We have a poster on Saturday comparing surprise ratings across all three experiments, including where they match and crucial differences in the why experiment, which is why we won't compare it here. So if you're interested, please stop by and hear more details then. So to compare the how experiment, first we calculated relative accuracy for participants in this experiment, looking at how likely people were to rate a violation scene as more surprising than the matched control, and aggregating across the broad scenario types. We find that ADEPT captures people's surprise best by a factor of 2 as compared to alternate models. And it's the only model that can differentiate all the scenarios above chance, like people can. Next, we investigate the timing of surprise. In this example scene, the cup travels out and back behind one screen, it's not seen in the middle, and then an identical looking cup travels out and back behind the other screen. Finally, the screens go down, showing that one cup remains. The plot on the right shows the cumulative number of times people and ADEPT registered surprise before that point in time. Here we see there are 2 times when people, the blue line, are surprised. Some people are surprised when the cup appears the second time, perhaps suggesting they thought the cup teleported. But most people are only surprised when the screen goes down, suggesting that they thought there were 2 identical cups and were surprised to see only one. You can see the ADEPT model, the red line, registers surprise at very similar times as people, although the rate it does differ slightly. Pulling out to a wider view, we can see that ADEPT generally finds scenes to be surprising at the same time as people across all 8 violation types, but we can see some slight differences in the timing or level of surprise across scenarios. We can also look at how well ADEPT extends to entirely novel scenarios. For this, we tested ADEPT on the IntViz dataset, a similar violation of expectations benchmark that tests models' performance on a set of physical principles similar to the ones we did. All we do to transfer ADEPT to the IntViz dataset is retrain the derenderer to allow it to extract objects from a new environment, new images, but we keep the dynamics model the same. Now, IntViz is also broken down into types of violations that it tests, and here we focus on their O1 dataset that tests objects' permanence. This is most closely matched to our create and vanish scenes. Now, we can see ADEPT achieves about 90% performance on our test scenes, but only about 67% on similar IntViz scenes. This is still far above chance, but it is a reduction in performance. So we looked into this, and it appears that this decrement is due to the difference in physics. IntViz uses a different physics engine to generate stimuli, and includes things like objects bouncing off of the floor that don't exist in our data set. Because ADEPT can't learn these new physics, these differences lead it to perform a bit worse without manual tuning, suggesting that the ability to learn dynamics on the fly is important for generalization of physical understandings to new environments. So next, let's talk about the other model, PodNet. But first, I'll review some developmental research that inspired it. One important cue for infants to pick objects out in the world is motion. So for instance, if 2 rods are sticking out from behind an occluder and they move in a disconnected manner, it's easy to see that they're separate. But if those same rods move in tandem, they're likely to be just 2 visible parts of a single longer rod. If we test infants' expectations using the same looking time and surprise measures, find that even 4-month-olds do expect the rods moving together to be a single object, despite never seeing them connected before. And this isn't just about some gestalt form completion. Even if the 2 objects look very different, infants expect them to be parts of a single thing if they move together. We use this principle as the basis of our next model. Assuming that object parts move together can provide a strong training signal to pick out objects from a scene. While ADEPT requires supervised training for its derender, this principle would allow a model to train itself in a self-supervised manner. Using this principle, we propose the Physical Object Discovery Network, or PodNet. This work is led by Yilin Du and is recently released on arXiv, so he deserves all the credit for the good parts, and the parts you don't like are probably due to my suggestions. PodNet works by taking an image, breaking it down into patches, and trying to discover what parts of that image belong to different objects or the background. It then takes these object segments and uses them along 2 paths. First, it extracts physical properties for each object, including the location, size, and orientation. Similar to ADEPT, it treats all objects as simple shapes. In this case, everything's a cuboid. It then uses these properties and learns how to simulate the next state of the world by comparing it to the extracted properties from the next time point, again, similar to ADEPT. This allows the model to learn to extract object representations that make useful predictions about the future. On the other path, the object segments are used to recreate the image using a component variational autoencoder. This ensures the representations contain rich 3D object information that constrains the physical predictions and ensures they don't degenerate. Together, these two constraints provide a strong signal for self-supervision to learn object representations and dynamics. We first look at how well PodNet picks out objects from images. In general, PodNet outperforms other state-of-the-art self-supervised object discovery algorithms like Monet and Iodine, as well as reduced versions of itself. We can see in particular one area where PodNet does better. Take, for instance, the inset on the right, where a block has just begun to peek out from behind the screen. Because this is a small, disconnected set of pixels, alternate models treat the box as part of the screen. PodNet, on the other hand, has tracked the box and realizes that these new pixels are more likely coming from the box coming out from behind the screen, as opposed to the screen growing a little bit. We can also look at how well PodNet generalizes to new objects. Just as with ADEPT, we held out some shapes from the training set and found that PodNet could easily identify them in testing. Similarly, we created novel objects with different colors by painting them in two separate colors. Most of the time, PodNet was able to recognize that these were a single object because those two colored parts were moving together, which is a hallmark of objecthood. Finally, we can look at how well the representations from PodNet react to physical violations, using the same measure of surprise as deviation between the dynamic model's expectations and its observations. For instance, in this block scenario, we see the screen go up to cover part of a wall, a box travels behind it, and the screen goes down to show the block on the opposite side of the wall. PodNet is able to discover object representations that are stable enough to identify where the box should be through occlusion, and so it's surprised when it appears in an illogical place. It doesn't quite reach the level of ADEPT on these scenes, but it still performs well over chance. However, one limitation is that this performance only occurs when PodNet is fine-tuned on the control videos from each scenario, so it still never sees any violations. This suggests that there's too little structure here. PodNet might be overlearning the dynamics of the training scenes, and so it doesn't generalize to the new physical scenarios as quickly as models with more physics built in. So in summary, we introduced two models here: ADEPT, which has a lot of structure and little learning, and PodNet, which has some structure to account for core knowledge, but much more learning about objects and dynamics. Because these models outperform alternatives with much less structure, it does suggest that core knowledge about physical objects is an important starting point for any human-like model of dynamics. But going back to the original question about how much structure versus learning is needed, the answer is likely somewhere in the middle of these two models. There must be the ability to learn new information about physical dynamics, but enough structure that allows for easy generalization of that knowledge to novel scenarios. Using some of the principles of probabilistic programming that Josh talked about this morning, we're now designing systems that can split the difference, that learn symbolic models of dynamics and their parameterization, which we hope will lead to a much easier generalization to novel scenes and physics types. So stay tuned for that. And so with that, I'd like to thank all of my collaborators on these projects, especially Jerry May and Shunyu Yao, without whom the ADEPT model would just never have been built, and Yilin Du, who's the brains behind PodNet. And finally, thank you all for listening.